We've made it to Module 3, Lesson 4, Confidence Intervals for Proportions. Let's start this one with an example. Consider this. Your local newspaper polls a random sample of 300 voters, finding that 160 will say yes when they vote for the upcoming school budget. So your paper has decided to poll a subset of your voting population there in the community in order to get a good idea of how people are going to vote when the upcoming school budget is voted upon. So you can see we're interested in what the sample proportion is. What is p hat? P hat is simply those who said yes divided by the total number that they surveyed. 160 divided by 300, which is roughly 0.53, or we could say 53%. The paper's aim in doing this is trying to use this value, again, to estimate how all voters will vote, the population proportion here. And this is a common technique used with groups wanting to know a population proportion here. They are interested in that, and they want to use a sample in order to estimate it. What we have to consider, again, is if they interviewed a different 300 voters, still randomly selected, but different individuals, they might not always get the same result. We would imagine that each sample of size 300 would give us slightly different or slightly varying results. We acknowledge that this variability exists, and we know that our estimate of 0.53 is just that, an estimate, and we want to incorporate the variability. So we're going to try to create a range of feasible values rather than just one number. Here's how we're going to do it. The first thing we need to do to make sure that we can compute this range is to make sure a few assumptions are met. The first thing we want to see if it's true is that the sample was a simple random sample, or we might just say a random sample. And we saw that the paper did choose a random sample. Next, we want to make sure the conditions for the binomial distribution are satisfied. Well, let's see if we can recall those. We want to make sure we have a two-sided outcome. Yes, we have that. The voters are either going to vote yes or no. The second one is that we have a fixed number of trials. Yes, the paper decided to interview only 300 people, so we have a fixed number of individuals. We want to make sure the trials are independent. In other words, each person's vote is independent of the next. I think that's easy to assume. And lastly, that the probability of a success remains constant from voter to voter. And I think we can assume that as well. The last assumption here we need to make is that the successes were at least 10 and the failures were at least 10. That is, we had at least 10 people that said yes and at least 10 people that will say no. If these aren't met, then we have to use an approach to do this. But in our case it was, so these all were met. So basically what this does is give us permission to use our normal model, our bell curve, to address the situation. This bell curve is going to help us create this interval or range of values. So here is our bell curve that we know we are allowed to use to solve this problem. As you can see, we have it centered about p hat, our sample proportion. Recall our sample proportion was 0.53. Now typically we would take our bell curve and center it about the population proportion, just plain p. But you know, we don't know that value in this problem, so we will take our distribution and center it around our sample proportion. Now oftentimes you've seen me after I've created this bell curve and found the center. I want to find the value that I've computed over here, which is going to be a standard deviation. In other words, it's going to help us determine how skinny or how wide our bell curve will be. Our standard deviation, which actually I'm going to call standard error with this problem, is the square root of p hat times q hat divided by n. Now, the reason we're calling this standard error rather than standard deviation is because we don't know the value of p and q, and we're using p hat and q hat as sort of a stand-in for them. So it goes from being standard deviation to standard error. Now, if we plug in the values we know, we have 0.53 for p hat and 0.47, that is the proportion of people that will say no, divided by the total number of people, 300. If you put that in your calculator, you can pause the video and try this, you will get approximately 0.03. Now I'm going to take that standard error and label the tick marks that are to the right, adding 0.03 at each hash mark. And likewise, I'll do that for the left. So we get a good idea of the center of our distribution and the range and spread of values as we go from right to left. Now recall, we used something called the 68, 95, 99.7 rule early on in the course. And if we go out 2 standard deviations, or in our case 2 standard errors in each direction, that'll capture 95% of the curve. So what this is telling us is that we are 95% confident that the true proportion of all voters that are going to vote yes on the upcoming budget is between 0.47 and 0.59, roughly between 47% and 59%. We're 95% confident that the true proportion, that is P, is somewhere between that range of values. So notice we aren't necessarily looking right at the 53% anymore. We're widening our scope, kind of like creating a net. And we think that it's the true proportion of all voters, the true population, is somewhere between these two values. Now this is called a confidence interval. And a confidence interval essentially is made up of a point estimate that's in the middle, that's our p hat, and we're going to go to the right a bit, and we're going to journey to the left a bit. And how far we go is called a margin of error. Now this might be a word you've seen before or heard before in the news, or when you're looking at a newspaper or a magazine article when they're polling people. This is called our margin of error. It's what we consider the maximum likely distance between the point estimate and P, or in our case the population proportion. You can see we're going to reach out to the right. We're going to go as far as this value here, which we call the upper confidence limit. We're going to go to the left and go as far as this value to the left, which is called the lower confidence limit. So a confidence interval is essentially a point estimate, that one number you get from your survey, plus or minus margin of error. We can even write it in more of a symbolic terms according to what we're working on. P hat plus or minus E. E for margin of error. Here it is again. Let's kind of expand upon this. This is the concept. This is specifically what we just did in our last problem. We took the sample proportion and we added, subtracted approximately 2 standard errors. Remember, we calculated this with the bell curve. A general confidence interval, now this is a 95% one, is essentially this here. A general confidence interval, all I've done in this case is trade out the 2 for a z value. We call it z star, a critical value. P hat plus or minus a multiplier here called a critical value times the standard error. So what this will allow us to do is change our confidence. Perhaps you might want to do a 90% confidence interval or a 99% confidence interval. These are all very popular confidence intervals. All you have to do in order to change your confidence level is to alter z star. Z star is for each of these very common confidence intervals listed here to the right. Notice here for a 95% confidence interval, one would use 1.96. We used 2 earlier in sort of an oversimplification of what we're doing, but a more appropriate value, a more exact value, is 1.96. That is, 95% of the values will be within 1.96 standard deviations or standard errors. We weren't lying to you earlier. We were just doing a wee bit of rounding, calling 1.962. For the rest of this module and the rest of the course, we will now begin to use 1.96. So, what if our journalist made a headline that read, "School budget will pass"? It might look like something below. How comfortable are you with this headline? I know our sample had more than half the individuals say yes, but this doesn't necessarily guarantee that this measure is going to pass on the day that they vote. You see, our true population proportion, that is the proportion that will say yes in our entire voting public, can be anywhere inside of this interval. We don't know where it is. Now, p-hat by design is in the middle. That's what our sample said. But our true opinion of all voters is we believe we're 95% confident it's in this range of values. Now, it could be on the right side of this interval, or it could be possibly to the left. We don't know. What we do know is our process that we use to create this interval is successful in capturing p 95% of the time. So if our p is indeed on the far left of this confidence interval, then the true proportion that will vote yes could be less than 50%, and the measure wouldn't pass. So we have to be cautious. When we're looking at information, we want to look beyond the point estimate and consider interval estimates. This is a great approach when you're critically examining things. Again, just to repeat what 95% confidence really means, because I know this is a new concept for us. So we know that each confidence interval uses a sample statistic to create it. And these sample statistics here are these little red dots. And each sample was going to have slightly different results. So that's why the red dots are sort of spread along here at different levels. And the confidence intervals are these blue lines that extend from the dots. See, this creates a range of values. So there are 20 confidence intervals that were created here to estimate a proportion. This is our proportion, the green line, the true population proportion. We're going to pretend we know what it is. And what is happening here is that roughly 95% of these will capture our true population proportion. In other words, the green line will be somewhere within the figure. You can see it fails here on our first one. It doesn't contain, it doesn't cross over the green line, nor does this one. But the vast majority, 95% of intervals that we could create would contain our true population proportions. So again, we're 95% confident in the process we use to conduct or to construct confidence intervals. Let's work an example. Alcohol abuse is a serious health problem on college campuses. A nationwide survey of students at 140 four-year colleges in the U.S. defined frequent binge drinking as having 5 or more drinks in a row, 3 or more times in the past 2-week period. Of the 17,096 students they surveyed, 3,314 met this criterion. Assume the data represents a simple random sample of four-year colleges. So the first thing we want to do is calculate the prevalence of frequent binge drinking on college campuses. And we'll also want to make a 95% confidence interval for this estimate. So before we get started here, let's just take a brief moment to consider if our assumptions are met that we need to have to use the normal model to help us with this. We do have a simple random sample. the criteria for the binomial are met, if you think about it, you're considered a binge drinker or you're not a binge drinker. I would hope that each college student's drinking habits are independent of the next, and there was a fixed number of students that they asked. I think we have the assumptions that need to be met in order to use our normal model. Okay, let's proceed. So what you see that I did here at the top of the screen is that I took the 3,314 students who qualified as binge drinkers and divided by the total number that they surveyed. This works out to just about 0.194. So 19.4% of students qualified as binge drinkers. The complement of that is 0.806 or 80.6 were not considered binge drinkers. Now they wanted us to use a 95% confidence interval, so this is that prevalence factor they wanted to know. The prevalence is about 19.4% students are binge drinkers. And they wanted a 95% confidence interval, so let's remember we're going to use 1.96 for Z star. So let's take this information and put it into our formula for a confidence interval for a proportion. Here's that formula from a few slides ago. And we're going to slowly start to plug in what we know. In this step, you can see I put the 0.194 for p hat, the 1.96 because we're doing a 95% confidence interval for Z star. P hat and Q hat go in the numerator of this fraction, and then we divide by the sample size, which is 17,096. Whoops. Let me fix that. I inverted a number here. All right. Don't worry, our calculations are right from there. That was just a typo. Okay, so we have this in here, and then we're going to take the right-hand side after the plus or minus, put it in our calculator and simplify it. This might be the point in the video where you're going to want to pause and try this on your own to see if when you simplify this mathematical expression here that it comes down to approximately 0.006. Try that real quick. Okay. The last part of this is to evaluate the plus or minus that are between these two quantities. So on the left and the right, I'm going to split it off. On the left, I take the 0.194 and subtract off the 0.006. And on the right, I take the 0.194 and I add on the 0.006. Now what 0.006 is our margin of error. So you can see I've added and subtracted it to what our sample told us. The results are 0.188 and 0.200. So if I take that and put it into a meaningful sentence, what it's telling us is that we are 95% confident that the true proportion of all college students that binge drink is between 18.8% and 20%. What I want to do next is show you how you can accomplish the same thing if you don't like using your calculator to manually calculate this. We can again use StatCrunch to help us with some of the busy work. So if you could open up StatCrunch, if you want to do this along with me, that's great. If not, you can just watch it and then try it later on your own. Open up StatCrunch to our spreadsheet, and we're going to navigate from Stat button to Proportion Statistics, one sample with summary. And once you navigate in, this pop-up box will appear. So what you're going to do is the number of successes, that's our numerator. And the number of observations is our denominator. So basically they don't want to know the 0.194 that we had earlier. They want to know what exactly was in your numerator, what were the number of successes, and what were the number of observations. And again, remember, success is just a word we use in statistics. It doesn't always mean the event is successful. I don't think any of us agree that binge drinking is a successful thing, but since this is what the researchers wanted to look at, this is what we consider a success. So we put that in. Then you have to click the bubble down here, make sure it's clicked on, and then you give StatCrunch the confidence level we want. And in this case, we wanted 95%. And you can put any level you want in here, 99, 90, 47. I don't think we'll use a 47, but this is a box that can be edited by you. Once you get those set, hit Compute, and what you'll see is a new pop-up box in the screen that looks like this. So you can see it summarized our results. It reminded us what our numerator was, what we entered as in the denominator, in case you notice you have a typo like I did earlier. What that works out to be is a sample proportion, so the count divided by the total is that 0.194 that we used. Here's our standard error. That should look like a familiar number. We doubled it, right? So that's where the 0.006 came from. We essentially doubled it. And we have our lower limit and our upper limit of our confidence level. These two numbers are essentially what you're seeking out. This is the 0.188 when rounded to 3 digits, and the 0.200 when we round to 3 digits. This is a reasonable, valid way of working the problem if you like this way, and you can use it on tests and quizzes and homework problems if you prefer to use StatCrunch. This is our last concept in this module. Often we are curious about how large of a sample we should use in order to get a reliable estimate of a population proportion. Here's a formula that could help us out. N equals Z star times P hat times Q hat, all divided by the margin of error squared. Now just a note, this formula didn't just come out of thin air. It's actually our margin of error formula solved for N. So what they did is they took this guy and through the use of several algebra steps, they isolated N. So this formula is something we've already used, we're just using it in a different way. So if you know the kind of confidence you'd like to have for your estimate, how big of a margin of error you would like to have, and possibly a value for P hat and Q hat, then we can figure out how large of a sample do you have to use. Here's an example. You've been hired by the Ford Motor Company to do market research, and you must estimate the percentage of households in which a vehicle is owned. How many households must you survey if you want to be 99% confident that your sample percentage has a margin of error of 3 percentage points? We're going to go ahead and assume that a previous study suggested that vehicles are owned in 86% of homes. So what we know so far is that we want 99% confidence for this, which means that our Z star, our critical value, is going to be 2.575. They mentioned that they wanted their margin of error to be 3 percentage points, thus E will equal 0.03. And finally, we're assuming that we can use a prior study that found out that 86% of homes had a vehicle, so we'll let P hat be equal to 0.86 and Q hat, the complement, 0.14. So if we plug these values above into our sample size calculation formula, don't forget to square Z star and E. Intermediate step here you can try with your calculator, see if you get the same thing. And if we divide it out, we discover that we get 897.03. Now, we have a little bit of a decimal value here. It's not exactly 897, and because this is here, we're going to have to round. Now we're going to do a strange way of rounding here. We're going to round up to 898, even though the decimal is only at 0.03. The reason we're doing this is because households are what we call discrete entities. We can't interview a fraction of one, and any kind of fraction of one. So in order to ensure our confidence and the kind of margin of error you're willing to live with, we have to take anything that's above this value and go up to the next whole number. 898 households. You'd have to get you and your team ready to go to interview almost 900 households. Now, here's part B. Assume there's no available information that you can use to estimate the percentage of homes that have a car. So when there's no available information for your sample proportion, that is P hat, then we often take the route where we'll let P hat and Q hat both equal 0.5. This will give us the the most conservative estimate of size, which is actually the largest, that will allow us to have the type of confidence we want and the type of margin of error. So when you don't know a value for p hat, which is often the case, then we just share the load. Let p hat be a half and let q hat be a hat. Now we're just doing the same calculation as before. We're just now using 0.5 here and here. Here's an intermediate step if you want to check it with your calculator. And that leads us to the value of 2,762.76. Again, we're going to round because we can't interview a fraction of a household. So we're going to have to interview 2,763 households in order to estimate the percentage of homes that have a vehicle, to do that with 99% confidence and a margin of error that's no bigger than 3 percentage points.